Right. Ladies and gentlemen, welcome to the invited lecture of Professor Raj Chetty. Allow me to introduce you Professor Raj Chetty briefly. Professor Raj Chetty is currently a professor at Stanford University and the director for Stanford Opportunity Lab. Professor Chetty's research combines empirical evidence and economic theory to help design more effective government policies. As many of us know, Professor Chetty has published in many top journals in economics. His work on tax policy, unemployment insurance, and education has been widely cited both in and out of academia. His current research focuses on equality of opportunity, and as one of the PIs of the Equality of Opportunity project, he uses big data to understand and identify new pathways to upward mobility, and how we can give children from disadvantaged backgrounds better chances of succeeding. Professor Chetty is a recipient of a MacArthur Genius Fellowship and the John Bates Clark Medal in 2013, given by the American Economic Association to the best American economists under the age of 40. He's a fellow of the Econometric Society and has won numerous awards for his research. Professor Chetty had held faculty positions at UC Berkeley and Harvard University and was also the editor of Journal of Public Economics and Journal of Economic Literature. Ladies and gentlemen, without further delay, please join me in welcoming Professor Chetty.
Thanks so much. So can everyone hear me? Great. So it's really a pleasure to be here. Thank you for the introduction, Wallace. So I'm going to start with this chart here by way of motivation for this talk and the broader research that our group is doing, which Wallace mentioned, on the Equality of Opportunity project. So what this chart shows you is what we think of as the fading American dream. So if you think about the American dream, what attracted many immigrants to go to America as the land of opportunity, one way that that was conceptualized historically is that America was a place where kids had, if they worked hard, a good chance of doing better than their parents did in terms of earnings at a comparable age. So what we're doing in this chart is combining various data sets. I'm not going to get into the details of this here, but essentially by linking census data to tax records, we ask what fraction of children, based on the year in which they're born, earn more than their parents did when we measure both their income and their parents' income roughly at age 30, adjusting for inflation, okay? And so what you can see is that for kids born in 1940 in America, it was a virtual guarantee that you were going to achieve the American dream of doing better than your parents. 92% of children born in 1940, by our estimates, earned more than their parents did when they were 30 years old. Now, if you look forward in time, there's a really stark trend here, where if you look at kids who are turning 30 today, who were born in the mid-1980s, it's essentially a coin flip as to whether you're going to achieve the American dream. 50% of kids are earning more than their parents did at a comparable age. So our sense is that this really steep decline in kids' chances of moving up relative to their parents underlies a lot of the frustration that we see in America, where lots of people express the idea in various ways that they're not able to do as well as previous generations. And so our research group, at a very broad level, has been thinking about how we can revive the American dream at the biggest picture level. That's the question we're seeking to answer in this, what we're calling the Equality of Opportunity project that Wallace described. And our method for doing that is to use big data or administrative data sets from various different sources to try to shed new light on this question. So we analyze a range of interventions as part of this project, from childhood to adulthood, looking at the effects of schools, higher education, colleges, and so forth. What I'm going to focus on here today is specifically the role of neighborhoods, which, as many of you might know, has been the subject of a long period of research in social science in both sociology and economics, going back at least 40 years or so, to famous work by William Julius Wilson and many, many others. But despite that long-standing literature, I think partly because of limitations in data and methods, basic questions about whether neighborhoods even matter, does where you grow up matter for your economic outcomes, and how exactly does it matter, what are the mechanisms through which neighborhoods matter, those basic issues remain unresolved. And in our view, this is one of the key things to think about in understanding how to more broadly increase intergenerational mobility in the US and reverse potentially that trend that I started out with. So in this talk today, I'm going to talk about work where we use data from de-identified tax records in the United States to present two sets of results on neighborhood effects. The first is quasi-experimental evidence that neighborhoods have significant causal effects on children's long-term outcomes in proportion to childhood exposure. So the key idea, as you'll see here in the data that emerges, is that the more years you spend in a better environment, and I'll make precise in a little bit what I mean by a better environment, but the more years you spend growing up in a better place, the better you do in the long run. There's this very clear linear relationship basically between childhood exposure to better neighborhoods and long-term outcomes. Second, building on the research design that we developed to establish that first point, we estimate more ambitiously the causal effect of growing up in every county in the United States. So we're going to estimate 3,000 causal effects, one for every county in the US, and essentially try to answer the question, if you put a given child in this county in Chicago versus some other county in California, what is the impact on that child's long-term outcomes going to be? So these results are presented in two companion papers, each of which focuses on one of the two things listed at the top. I'm going to briefly summarize the results from the first paper with the quasi-experimental design so I can spend more time on the second paper where I really think there's rich information and potential pathways for further work. Okay, so let me tell you briefly about the data we're using for all of this analysis. So we use de-identified data from federal income tax returns in the US spanning 1996 to 2012. So this is an incredibly rich database of the type that I think is revolutionizing applied microeconomics more broadly. In this case, this is a data set that covers every single person in the United States over, at the point we started this work, a 17-year period, and every year as people file their tax returns, you have additional data. So it's really incredible breadth of coverage, a population-level panel data set unlike what we've been able to work in the past. And you'll see why that is incredibly useful for what we're going to do here. So using these data, we are able to link kids to parents based on who people claim as dependents on their tax returns. And then in what I'm going to show you here today, we're going to focus primarily on kids born between 1980 and 1986. There are about 4 million kids born per year in the US, so that's about a sample size of 25 million children in what I'm going to be showing you. We're going to characterize neighborhood effects at two levels of geography. By commuting zone, commuting zones, think of them as essentially analogous to metro areas. They're aggregations of counties based on commuting patterns, and then also at the county level. Now you might think intuitively, for those of you who know US geography, counties are quite big. They comprise many towns, and when most of us think of our neighborhood, we think about a much finer geographic unit than the entire city of New York or the entire city of Chicago. So the way we are conceptualizing this is using a hierarchical model where we're starting at broad geographies, and as I'll show you at the end, we're zooming in finer and finer down to the block level by geocoding the entire population. But today I'm going to show you results at the commuting zone level and the county level. We divide the sample that we're going to use for the analysis into two parts. A group of people I'm going to refer to as permanent residents, people who do not move, whose parents do not move. So parents who stay in the same commuting zone or the same county from 1996 to 2012. And then a separate set of people, the complement of that set of people who are movers, people who move between areas, okay? So let's start by looking at the data for permanent residents. And just for illustrative purposes, I'm going to start by showing you the data for kids who were born and raised in Chicago, for children born specifically in 1980, okay? And so what this chart is plotting is the conditional expectation of the child's rank in the income distribution relative to all other kids born in the same year. So when we define percentile ranks for kids, the way we're doing this is take all the kids born in 1980, rank them based on their incomes measured at age 30 in this case, from 1 to 4 million, and convert that to percentile units. So we're ranking you relative to other people of the same age to take out life cycle effects. So that's what's on the y-axis, the mean rank of the kids, conditional on the parents' rank in the national income distribution. So one other thing to note here, just for clarity, I'm going to talk about data across various local areas, but I always rank people in the national income distribution, not relative to other people in their own area, okay? So what this chart is showing is 100 dots here, one for each percentile of the parent income distribution, and we're just plotting the mean child rank conditional on the parent's rank. You see a very clear upward sloping relationship. This reflects the fact that there's intergenerational persistence. If you're born to richer parents, you're richer yourself on average. The other key property you see here, which turns out to be incredibly robust, not just in Chicago, but in any subsample we've looked at, is that this conditional expectation in rank space looks almost perfectly linear. And so the fact that it's linear is quite convenient from a statistical perspective, because it means, of course, that we can summarize the conditional expectation at any point with two parameters, the intercept of this line and then the slope of the line, the rank slope. So if I just estimate the slope and the intercept of the line using a linear regression in each area, I can then tell you what the conditional expectation of the kid's percentile rank is given the parent percentile for any percentile p, because it's just going to collapse to those two parameters, of course. So we do that exercise for every commuting zone in the United States and construct this map here, which shows you the geography of intergenerational mobility in the US. So what this is the predicted income rank at age 30 for children with low-income parents, with parents at the 25th percentile of the income distribution, just to pick one percentile to summarize the data for low-income kids. And the map is colored so that the redder colors represent areas with worse outcomes for low-income kids. So you can see, for instance, in parts of the deep south in the US, if you're born to parents at the 25th percentile, on average, you end up below the 38th percentile of the income distribution. But if you look in comparison at the lightest yellow colors on this map, places like in the middle of the country or the West Coast, a number of those kids who start out at the 25th percentile end up well above the median, above the 55th percentile of the income distribution on average. So there are really substantial differences in kids' outcomes across areas based on where they grow up. And this is just in observational data, right? Looking at kids whose parents do not move across places. So the question we ask in the first paper I'm talking about today is, what is the average causal impact of growing up in an area with better outcomes? So this variation in observational data, of course, could reflect either the causal effect of growing up in a different place for a given kid, or it could reflect selection. The set of people who live in the center of the country are different from the set of people who live in the southeast. So maybe this doesn't have anything to do with the causal effect of neighborhoods. Maybe it's just about different people living in different places. And so that's the first key question we're going to answer. On average, if I move you from a red-colored place in this map to a lighter-colored place on this map, how much are your outcomes actually going to improve? How much of this variance is due to the causal effect of places? So how are we going to identify that parameter? That's something, as I was saying, social scientists have been interested in understanding for a very long time from a statistical point of view, knowing how much of the variance in outcomes we see is attributable to where people grow up or the environments they experience. So we're going to identify the causal effects of neighborhoods by analyzing movers' outcomes. And critically, we're going to exploit variation in the timing of moves to separate the causal effects of exposure to better areas from selection effects. So we recognize, of course, that if you look at people who move from, say, Chicago to New York, that's going to be a non-randomly selected set of people. And so you can't just compare the outcomes of people who chose to move to New York with the outcomes of people who chose to move somewhere else. You need to do something more sophisticated than that. And what I'm going to show you in particular is if you exploit variation in the timing of the moves, you can, I think, quite credibly isolate the causal effect of the place relative to selection effects. So to show you how that works, let me start by considering the subset of families who moved with a child who is exactly 13 years old, just to pick one example, and you'll see how we generalize this in a second. So what we're going to do is regress the child's income rank in adulthood, which I'm going to call YI, on the predicted outcomes of the permanent residents in the destination, which is Y bar PDS in this equation, P denoting the parent's income percentile, D denoting the destination area, and S denoting the child's birth cohort, okay? Now you'll notice that in this equation, we include a set of fixed effects for the parent decile by origin by birth cohort, so that we are identifying this key coefficient B sub M purely from variation in the destinations to which people go. So the way you want to think about the thought experiment here is take two people who say start out in Chicago, one of them moves to New York, one of them moves to San Francisco. How did their outcomes compare in adulthood if they move at age 13? And the answer to that is shown by this plot here. So what this plot is showing on the x-axis is the predicted difference in the child rank based on the permanent resident outcomes in the destination versus the origin. So if you take, for instance, start at the far right with the +6, those are people who are moving to a place where the permanent residents have 6 percentile better outcomes on average relative to the place where they started. So this could be, for instance, a person moving from a place like Dallas, which is an average place in our data, to a place like San Francisco, which has quite good outcomes, was a relatively light yellow color in the map that I showed you. So the people on the right here are moving to better places based on the permanent resident outcomes. And then the people on the far left, the -6, they're making the opposite move. They're moving to one of the redder colored areas, right? And so what we're plotting is after taking out those fixed effects that I showed you in that equation, the mean residual child rank in the national income distribution for the families that actually moved. And the way this plot is constructed is it's a binned scatter plot. So we divide the x-axis variable into 20 equal-sized bins and plot the mean of the y variable and the mean of the x variable within each of those bins, just to give you a non-parametric representation of what that linear regression specification looks like, what that conditional expectation looks like. And you can see very clearly that among the people who moved when their kid was exactly 13, if you move to a place where the permanent residents are doing better, your own child is doing better in adulthood. And if you move to a place where people were doing worse, your own child is doing worse in adulthood, right? So that is at least superficially consistent with the idea that it matters where you grow up. Now, of course, that's not enough to conclude in and of itself that neighborhoods have causal effects, because there could be serious selection biases correlated with where people choose to move, as I said before. So the thing that I want you to note here is that the slope of this relationship is about 0.6. That is, if you move to a place where the permanent residents are doing 1 percentile better, your own child ends up 0.6 percentiles higher in the income distribution if you move exactly at age 13. So now what we're going to do is generalize that analysis to look not just at age 13, but all the various other ages that we're able to examine in the data. And it turns out, because of data constraints, the earliest age we're able to look at is age 9 at the moment. So what this chart is plotting is that's the same slope that I estimated in the previous figure of 0.6 at age 13. So you see that point, right? If you look at age 13 here, you see that value of 0.61 plotted there. So we're running that same regression that I showed you in the previous slide at all the other possible ages of move, okay? And so you can see that there are two very clear points that emerge from this figure. First, until about age 23, those slopes clearly decline. The later you make the move to a better place, the less of a gain your child seems to get, or the later you make a move to a worse place, the less harm is done to your child. Okay, so these impacts of moving to a better or worse place are clearly related to the age at which kids are moving. The second thing you see is even if the parents move to what appears to be a better area when the child is, say, 30 years old, this is actually after the point at which we're measuring kids' incomes here. In this particular analysis, we're measuring kids' incomes at age 24. We show in the paper that the results are not sensitive to the exact age at which you measure kids' incomes. But in any case, so here, you see that even if you move, after age 24 at, say, age 27 or something like that, you still have a positive coefficient, right? So that shows you that that can't be entirely a causal effect, because if your parents move to a better place when you were 28, obviously that can't have a causal impact on your earnings at age 24. So the fact that that coefficient is not zero is consistent with the idea that there's selection in where people move. And so the key assumption that we are going to make in our analysis in order to isolate the causal effect of places is that that selection effect that we see on the right-hand side there, we're going to assume that that is constant at all ages n. So to the extent that the type of people who move to, say, New York are different from the type of people who move to Atlanta or San Francisco, that selection effect, the critical assumption we're going to make in our analysis is we're going to assume that to the extent that selection exists, as it appears to, it does not vary with the age of the child at the point of the move. You can see intuitively, if you make the assumption that the selection is constant at this horizontal line, then the difference between the points that you estimate and that horizontal line, Bm minus that selection effect delta, is going to identify the causal effect of moving to a better place at a given age m, right? You're effectively taking out the selection effect by estimating it at older ages and assuming that it's constant across all ages. Okay, so now obviously this is a pretty strong assumption to be making, that the degree of selection doesn't vary with the age at move. And so let me just talk about why you might worry that this assumption might be violated. So one intuitive thing that you might think is a concern is maybe the people who move to better areas, say San Francisco when their kids are younger, they figure out that wherever they lived before is not so good for their kid, and that's why they move to a better place at a younger age. And if those people tend to invest in their kids in other ways, they're investing in their human capital in other ways by trying to send them to better schools or reading to them more or whatever it is that we don't observe in the data, then you're going to have a confound in this analysis where the people who move at earlier ages, there's going to be a larger selection effect there, and that's going to violate this assumption. So that's one example of why you might worry that this assumption doesn't hold in practice. So we spent quite a bit of time showing in the paper that we think this assumption does actually hold, and let me show you a couple of examples of why we reached that conclusion. So we take 3 different approaches to evaluating the validity of that critical constant selection effects assumption. The first is that we compare siblings within the same family in order to take out family fixed effects. So the type of story that I just described to you, that more sophisticated parents move to better areas at young ages than less sophisticated parents, that gets eliminated if I compare 2 siblings within the same family, right? Suppose you move from Chicago to San Francisco with a 9-year-old and a 13-year-old, and you compare the 9-year-old's outcome to the 13-year-old's outcome, then you've eliminated the family level confounding factors that you might be worried about. And so this chart here replicates what I showed you before, now with family fixed effects. So you're identifying purely off of sibling comparisons within families, and you see the thing looks virtually identical. In fact, it's very intuitive what happens. The selection effect ends up going to 0, and the slope of the relationship ends up remaining at minus 0.04. That is a 4% rate of convergence to the destination outcomes for each year of exposure, okay? So that's consistent with the idea that this is not just driven by biases in the types of families moving early versus late. This actually is plausibly driven by the causal effect of the place. Now, there's another set of biases you might worry about that are not taken account of by the family fixed effects, which is that there could be another contemporaneous shock that affects kids in proportion to exposure time to the new area that occurs when the family moves. So for instance, maybe when a family moves to San Francisco, it's when they've gotten a positive wealth shock or had a change in marital status or something else. And it's not San Francisco itself that's making kids do better. Maybe it's that other thing that triggered the move that ends up affecting the kids, okay? So in order to deal with that, we do a couple of other things. One, which is familiar from this quasi-experimental literature, is we essentially look for instruments that induce certain sets of moves. So for instance, we look at moves induced by displacement shocks like local plant closures or natural disasters like hurricanes, which make a lot of people move out of a place. And you can see how that effectively gives you exogenous shocks in terms of at least the set of people who are moving. And we show that in the subsample of people who are displaced rather than voluntarily choosing to move at a given point, you continue to find very similar exposure effects. What I actually think is the most compelling piece of evidence, what convinced me that it really looks like neighborhoods have causal exposure effects, is this third piece of evidence, where we implement a set of what we call outcome-based placebo tests, or basically think of them as over-identification tests of the model, where we exploit the fact that there's a lot of heterogeneity in place effects across subgroups, by gender, by birth cohort, and by quantile. So to give you an example, there are some places that are particularly good for boys in America, and there are some places that are particularly good for girls. On average, places that are good for boys tend to be good for girls as well, but there are some divergences between the two. So for example, the city of Baltimore, which is known to have a lot of gang violence, tends to be much worse for low-income boys than low-income girls, because they tend to have very negative outcomes, all right? So what we show is, take a family that has a son and a daughter, and suppose they move to a place that's particularly good for boys relative to girls. What you find is that their son's outcomes improve in proportion to the number of years they spend there, while their daughter's outcomes don't change. So if you think about whether some other confounding factor could have generated the same pattern, that other shock, the wealth shock or whatever it is, would have had differential impacts by gender that happen to be correlated with exactly the impacts of the permanent residents, the outcomes of the permanent residents that we see in the destination area. That seems somewhat unlikely, right? More generally, we show the same kind of precise convergence pattern across quantiles of the income distribution and across birth cohorts. That is, your outcomes converge exactly to the outcomes of people born in the same year as you, and not the year before, not the year after. So if you think about the type of information people would have at the point of the move, it seems implausible that you'd get that kind of very precise convergence based on other selection or omitted variable effects. So I'm not going into the details of exactly how we do this analysis, but that's the high-level summary of why we end up being quite comfortable with this identification assumption of constant selection effects, and why we end up concluding that neighborhoods seem to have clear causal effects on kids' outcomes. The key punchline from the analysis in the first paper is that every extra year you spend in a place where people earn, say, $1,000 more in adulthood, your own outcomes converge to those people's outcomes at a 4% rate. And that relationship, as you saw in the figures I was putting up, looks roughly linear. Each additional year seems to contribute roughly equally. Okay, so that first analysis establishes that neighborhoods matter on average, but it does not tell you which particular places are really good for kids or what their characteristics are. What are the mechanisms through which neighborhoods actually affect kids' outcomes? So I think this is really important, because if you tell the average person on the street that you've done careful statistical analysis to show that where you grow up really seems to matter, the reaction is, that's like not that mind-blowing. That would have been my intuition to begin with anyway. What's more interesting is like, where should I actually be living in order to have better outcomes for my kids? And so that's what we're after here in the second paper. So what we're going to do here is estimate the causal effect of each county on children's earnings. So notice here that our goal is to estimate about 3,000 treatment effects, one for each county in the US, instead of one treatment effect, that 4% number, the average exposure effect that we estimated in the first paper. So it's a much more ambitious exercise than what we started out with. We're going to build on that timing of move design in order to identify these 3,000 causal effects. Okay, so the way we do this is in a series of steps, and I'll just outline in the interest of time at a high level what we do and then show you the results. So we begin by estimating the effect of each county using a fixed effects model that is identified using variation in the timing of moves between areas, exactly the same logic as what I was showing you earlier. So not comparing people who move to different places, but rather comparing people who make the same move, but at different ages, at different points of their child's life cycle. So to understand the intuition for how this fixed effects model is going to be identified, let's take an example, which actually turns out to be true in the data. So suppose kids who move from Manhattan to Queens, a different borough in New York City, at younger ages earn more as adults. So suppose people who make the move from Manhattan to Queens at younger ages, when we look at them in adulthood, they end up doing better. Then based on the logic that I was describing to you earlier, you can infer that Queens seems to have a positive exposure effect on kids relative to Manhattan. Because apparently the earlier you leave Manhattan, the better you end up doing in adulthood. So now you can make that kind of pairwise comparison for every move in the data, right? From Manhattan to Queens, from Manhattan to the Bronx, from places in New York to places in Chicago, and so forth and so on. So you have this 3,000 by 3,000 matrix of pairwise exposure effects. And essentially, we're going to collapse that onto a vector of causal effects of each place, assuming an additive structure, basically. So the causal effect of moving from A to B is the effect of B minus the effect of A. We're not going to allow for pairwise impacts in this simple analysis that we're doing here, okay? That's the key structure we're going to impose on the problem to make it tractable. So just to give you a little bit of detail, and it's fully described in the paper, so what are we doing here? We're estimating the place effects, this vector mu with n places, using fixed effects for the origin and the destination. That's what's shown in the brackets here, interacted with exposure time, the number of years you spend in the origin versus the destination. So that's the TC minus M term. And then we allow these place effects to vary with the parent income rank. So motivated by that linear relationship that I showed you at the beginning for Chicago, we're going to allow the causal effect of each place to have an intercept term and a term that interacts with the parent rank. This is just allowing for the possibility that the places that are good for the poor may not be the same as the places that are good for the rich. The causal effects of places could vary based on parent income, right? And then finally, the last term in that equation, we're going to include origin by destination fixed effects so that the model is identified purely from variation in the timing of moves and not where people are moving, based on exactly the logic that I was showing you before, all right? So what do you get from estimating those fixed effects? So you get a bunch of estimates, one for each county that are being plotted here, and I've highlighted some of them for the larger cities. On the y-axis are these causal effect estimates based on the movers, the causal effect of one more year of exposure on the child's mean rank in adulthood. And on the x-axis, we're plotting that against the mean rank of the children of permanent residents, the non-movers, at the 25th percentile of the income distribution, okay? And these two things are positively related. That makes sense because that was exactly the result of the first paper, right? That when you move to an area where people are doing better, the people who already lived there are doing better, you yourself do better on average. So you would expect these two set of estimates to be positively correlated based on the results I showed you earlier. Now, a key issue in thinking about how to interpret these estimates, which turns out to be critical in this analysis, is that there's quite a bit of noise in these estimates, as shown by these confidence intervals. So in some cities, like in New York or Los Angeles, you get relatively precise estimates just off of the movers. But in most cities, you don't have enough people moving in or out to get a really precise estimate of the causal effect purely from this data. And so that's going to motivate a lot of the methodology that we use in what follows, okay? So we're going to take these fixed effects estimates that come out of that model, which we interpret as basically noisy estimates of the causal effect of each place, and we're going to answer 3 questions using those fixed effects, which is what I'm going to talk about in the remaining time. First, we quantify the size of place effects. How much do places matter for kids' long-term outcomes? Second, we construct forecasts, mean squared error minimizing forecasts, that can be used to guide families that are seeking to move to opportunity. If someone comes to you and says, I want to move to a place where my kids will do better, what is the best place to move? We'd like to have an answer to that question. As I'll show you, that's very relevant for policy discussions in the US at the moment. And then finally, we'd like to say a little bit about mechanisms by characterizing what types of areas produce better outcomes in order to provide guidance for place-based policies. If you want to improve a given area, what types of investments should you be thinking about? So let me talk about each of these 3 things in turn. So first, to estimate the magnitude of place effects. So conceptually, what you've got here is a set of noisy estimates of latent parameters, right? The underlying causal effect of each place. So you can do a simple variance decomposition because you know the amount of noise in each estimate. You've estimated that. That's the standard errors, essentially. So if you subtract out the total variance, subtract the noise variance from the total variance of the fixed effects, you can extract the signal variance, the underlying variance of the latent causal effects of place. That is how much neighborhoods actually matter, okay? Now, to make the units more easily interpretable, rather than showing you these estimates in percentile rank terms, which are a little bit hard to think about, I'm going to translate things to percentage terms. And so just as a conversion, note that a 1 percentile change in earnings in the middle of the income distribution in the US corresponds to roughly a 3% increase in earnings. Okay, so I'm going to use that scaling in what I show you here. Okay, so once we do this analysis, what we find is that for children with parents at the 25th percentile of the income distribution, so low-income kids growing up in low-income families, growing up in a 1 standard deviation better county from birth will increase your earnings by 10%. So quite a substantial impact if I literally just take you from where you are to a 1 standard deviation better place, which in principle seems like a feasible move, that's going to increase your earnings by 10%, have a causal effect of 10% on your earnings. If you do the same thing for a kid at the 75th percentile, move them to a county that's 1 standard deviation better for high-income kids, you get a 6% earnings gain. So a smaller impact. This reflects a result we find in many settings in our work, that where you grow up matters more if you're poor than if you're rich, which I think makes sense intuitively. Rich people are sort of able to insulate themselves from local conditions by sending their kids to private schools, et cetera, so the neighborhood maybe ends up mattering less. Now, final point that's interesting when you think about the variance-covariance structure of these fixed effect estimates is you can look at the correlation of the fixed effect estimates for the low-income kids at the 25th percentile and for the high-income kids at the 75th percentile. And what you end up finding is that that correlation is actually slightly positive. And this is very important because it suggests that the places that are better for the poor are not necessarily worse for the rich. So there's no kind of zero-sum thing where if you have a place that's making more investments to help poor kids do better, that comes at the expense of the local high-income kids. In fact, we find a slightly positive correlation here, which I think is somewhat encouraging for policies that try to improve out neighborhoods for low-income kids. Okay, so that just tells you at a broad level how big these place effects are. Now, the next thing we're going to do is ask what are the best and worst places to grow up. So here, we construct forecasts that minimize the mean squared error of the predicted impact for a family moving to a new area. And the reason we do this is that the raw fixed effect estimates have relatively high mean squared error, that is, they provide relatively unreliable predictions because, as I was saying, especially in smaller places, they have quite a bit of sampling error. So we are going to reduce the mean squared error essentially using a shrinkage procedure. You can think of this as an empirical Bayes estimator, where we combine the fixed effect estimates, which are unbiased but imprecise, with the permanent resident outcomes, which are biased by selection because people are not randomly assigned to places. So they're biased, but they're very precise because there are large samples in each place. So intuitively, you can combine those two things to get a more reliable estimate, okay? And so just to show you graphically how we do that, so here's the same plot I showed you before of the causal effect estimates from the movers versus the permanent resident outcomes. You see that upward sloping relationship. You see the confidence intervals. So what we're going to do is the causal effect point estimates are somewhat noisy. So we're going to use the forecast based on the permanent residents, which are the projections based on this line. And we're going to take a weighted average of the blue dot and the green dot. That's conceptually what the shrinkage estimator is doing, putting more weight on the blue dot in bigger places, basically where you have a more precise estimate, where you have a smaller confidence interval. So in a place like New York, the red dot is going to be very close to the blue dot. In a small place like Raleigh, North Carolina, you're going to put a lot more weight on the permanent resident outcomes. You can see intuitively why that's going to minimize errors. So what do you get out of that analysis? So here's one example. So this map shows you our preferred estimates of the causal effect of growing up in each county in the New York City metro area. So to take one example, we estimate that if you grow up from birth in the Bronx, you will earn 10% less than in the average county in the US. If you moved across the Hudson River to Bergen County, New Jersey, you would earn 14% more than in the average county in the US. So that move of moving across the Hudson River would increase a low-income kid's earnings by 25% based on this analysis. Okay, so more generally, you can interpret each of these estimates as the causal effect of putting a kid in each of the different areas. And so we have these estimates for all counties in the US. So this is a list that shows you the best places to grow up in America for low-income kids and the worst places. So at the top of the list is DuPage County, Illinois, which is the western suburbs of Chicago. At the bottom of the list is the city of Baltimore in Maryland. And if you move from one to the other, we estimate something like a 30% swing in your earnings. So I've got just a couple minutes left. Let me briefly talk about the last thing that we do with these estimates. So we want to talk a little bit about what the characteristics of these of the good areas are. There have been a number of prior studies that have documented correlations between children's outcomes and various observable factors in observational data. So for instance, we see that children who grow up in ghettos with concentrated poverty tend to have worse outcomes. Now, those correlations that have been documented in the prior sociological literature, are they driven by causal effects or are they driven by selection? So that is growing up in a segregated area actually bad for a given kid? Or is it just that the people who live in these very places with a lot of concentrated poverty, they have worse unobservables and they have worse outcomes as a result? So we can answer that question by correlating our causal fixed effect estimates with the observable characteristics of areas and show how much of these correlations are due to selection versus causal effects. And so I'm going to show you that final set of results with this chart here. So what's being plotted here is the effect of a one standard deviation in various covariates, starting with an index of racial segregation on the child's expected percentile rank. And we're showing in the dashed line here the impact that you see in the observational data if you use the permanent residence outcomes to do this correlation. So now we then decompose that correlation into the part that's due to the causal effect of putting a given child in a place with a 1 standard deviation higher level of segregation, for example. That's based on the fixed effect estimates. And then what's left over, you can interpret as the effect of selection. So in this case, you can see that the majority of the correlation between racial segregation and kids' long-term outcomes is driven by the causal effect. That is, putting a given child in a place that is more racially segregated is harmful for that kid, okay? Now, more generally, when you look at a variety of other factors that we've documented and others have documented in previous work, you see that growing up in places with higher inequality as measured by the Gini coefficient, higher top 1% income shares, those are detrimental. Growing up in places with more social capital, so more socially cohesive community, more religious participation, those places have very positive effects. Places with worse schools as measured by dropout rates have more negative effects. So you can see a lot of the correlations that have been previously documented are primarily driven by causal effects. Now, if you look at a different set of factors, more demographic factors, like the fraction of single parents in an area, the fraction of immigrants, the fraction of black residents, here those dashed lines start to become much bigger, and selection appears much more important. That makes sense. When you're looking at characteristics of places that primarily reflect demographic factors, selection seems to play a more important role than when you look at things like the quality of schools or the degree of residential segregation. Now, one last thing I want to note here, even though selection is important when you look at factors like the fraction of black residents, the causal effect is still quite big. And so what that means is that black kids in America, on average, grow up in significantly worse neighborhoods than white kids in America. And so we estimate, based on this result, that 1/5 of the well-known black-white earnings gap is explained purely by the fact that blacks grow up in worse counties than whites, okay? Showing you that, again, these neighborhood differences seem quite important for economic outcomes and inequality. So if I can take one more minute, one last thing. So from an economist perspective, you might wonder, okay, so you show some of these places seem to have better outcomes than others. How much does it cost to live in a place that produces better outcomes for kids? So the last thing I'm going to show you here is we correlate our estimates of the causal effects of place with house prices or rents in each area. And the basic finding here is that there's not that much of a correlation. So for instance, here's the data for New York City, which I showed you before, plotted on the y-axis, the causal effects of each county. And here are the median rents. And so you can see there's somewhat of an upward sloping relationship, but there's a lot of variance around that line. And so in particular, if you look at Manhattan versus Hudson County, for example, those two places cost about the same amount on average for low-income families. But Hudson County has dramatically better impacts for kids than Manhattan, which means that Hudson County is basically like an opportunity bargain. It's a place that's relatively cheap, but produces good outcomes for kids. And I think understanding what's going on here, we think part of it might have to do with information problems, is an important area for further work. So let me conclude. I think the findings from this analysis provide support for place-focused approaches to improving economic opportunity. That is not just tackling that trend that I started out with at the national, federal level, but at the local level. And there are two ways that you can go about doing that. One is by helping low-income families move to better areas without paying higher rents. The outcome-based forecasting approach developed here provides a scalable method to identify such areas. And second, since you can't possibly move everyone, that can't be the solution, especially when you take general equilibrium considerations into account. You also need to understand what the recipe for success is in places that are currently producing better outcomes. Our sense from what we've done so far is that the places that produce better outcomes tend to have a common set of characteristics. They're less segregated, they have better schools and so forth, which suggests that their successes may be replicable in areas that currently offer lower levels of opportunity. So going forward, we think there are two key directions for future work. The first is to figure out how to help families with housing vouchers move to better neighborhoods. And so we've set up a partnership with the Housing and Urban Development Agency of the US government and 15 large public housing authorities, where we're trying to take the $45 billion a year that the US government currently spends on housing vouchers and help families getting that assistance actually move to places that will help their kids do better. And second, figure out more precisely how to improve neighborhoods with low levels of upward mobility. And so one thing we're doing in order to figure that out is develop estimates at finer geographies to study the impacts of local place-based policies. And so I will end with this. This just gives you a sense of where we're going with this. I showed you data at much more aggregated level by county and by commuting zone. This now is a map of estimated causal effects of growing up in each census tract within the Seattle area, which is where we've started out with this analysis. And so in the coming months, we're hoping to produce this for every census tract in the United States, so you'll be able to see in great detail how kids do in every block, and then try to figure out how you can improve outcomes going forward. All of this data, I should note, is publicly available on this Equality of Opportunity Project website for people who want to analyze this information going forward and work on these important issues. So I'll stop there. Thank you.
So thank you, Professor Chetty, for this wonderful talk. So now we have a souvenir for you. May I invite Professor Junsen Jan, Chairman of the Department of Economics, to present a souvenir for Professor Chetty. Thank you very much. It's time for coffee break.